The blue guys, they're orthogonal because they're using different resource block. So
they're not orthogonal on the capacity C. Right. And the backhaul.
They're also orthogonal on the capacity C, but they are
not in terms of capacity.
Yeah, they're orthogonal in terms of sharing.
It's a shared.
It's somehow it's like they are sharing the bandwidth on the wireline backhaul.
Exactly. So now the question is how to distribute the capacity C between CA and CB. So that's the question?
Yes.
So the orthogonal because they use orthogonal codes.
For example, I'm thinking of object. Object based
channels.
Yes.
Different subcarriers.
Different subcarriers.
Different subcarriers.
Okay. A resource block in LTE is 12 subcarriers.
So you don't have multiple users in the same subcarriers using the same.
Yes, you do. The two blue ones are in the same.
But is that all of it, or is there be more?
I assume that among
each
inside the cell,
on its side there is the 12 subcarriers to one user.
That's what each one is. You're assuming right now, right?
Yeah, assuming full frequency reuse. So for one resource block for each resource block, every inside all cells, there are some users that are using that resource block, which will cause unit cell influence. So my question here is, how do I distribute this backhaul incapacities in an optimal way so that the total throughput is maximized? So basically, I just want to maximize the total throughput subject to CA plus CB equals to C. And this is actually convex because this summates their convex functions, their linear functions of C and CB. They're actually concave functions of C and CB, approximately linear. This is linear. Yes, and the CA plus CB equals D is a linear function, so this is convex. So actually, you can think of even a simpler 3D algorithms to work. Because I would like to always allocate the backhaul capacity to the users, to the resource block with larger gain. Because previously I said that at different channel gains, the gain from receiver coefficient is different. So I would always allocate the coefficient probability to the subsystem that has larger gain from receiver coefficient first, and then
larger gain in what sense?
In
capacity gain,
yeah, that's what sense. So there will be more issues when I allow joint scheduling with these resource blocks. So now I'm assuming that first I schedule the resource blocks, and then I schedule the backhauling capacity. But if I allow joint scheduling among the resource blocks and the backhauling capacity, then the problem becomes non-convex. It becomes more complicated, and there will be there will need some future works about that. Also,
that's that bullet that I just was missing. Fairness.
It's fairness. Fairness is very important because, as I said in the previous, or maybe I missed, but actually, the gain from receiver coefficient becomes smaller as INR becomes comparable with SNR, which is indicating that cell edge users are getting smaller gain from receiver coefficient. So if I use this greedy algorithm, then the cell edge users is not going to get much benefits from this receiver coefficient because I'm going to assign fewer and fewer backhauling capacity to it. But in practice, it's the it's the cell edge users who need the
capacity boost.
Capacity boost. Yes, exactly. So that becomes a fairness issue. So waiting at the inside the system throughput, here I just put the same weighting for all the resource blocks, but you may want to put different weightings for that. And that would address the fairness issue. But if I separate no matter what, if I separate the process of the scheduling among the resource blocks and the scheduling of the backloading capacity, if I separate that, then it's still a convex engineering problem which can be solved efficiently. And so, like, my presentation is coming to closing to the end. So I'll just say something about the channel state information and the transmitters. So this is required to facilitate partial inverse cancellation, and however we will have imperfect CSIT. For TDD systems, you may get the CSIT by channel reciprocity, but current systems are mostly FDD systems. So we have to utilize feedback to get a more precise channel state informations and the transmitters. Okay. But as I said, in this particular simple two-user examples, we only need the strength of the channel. We don't need the phase of the channel. And even in TD systems, even in the FTD systems, the channel strength is roughly reciprocal among the uplink and the downlink. So that's not a huge problem. But for three-user channels, we will need more precise information for phases to get the partial inverse cancellation. In the three-user channel, more than three user channels.
Yeah, but we only need the downlink information. No, we will just need exactly. We need the terminals to tell the base stations what the channel looks like.
Yes, no matter in uplink or downlink. So
Why? Why the uplink? What kind of tree coding will the terminals do so that the channel state information makes such a big difference?
In the three-user channel, it's not sufficient to get only the channel name. You need the phase as well.
In the uplink.
Not yes.
But in the uplink, the terminals are transmitting pilots anyway.
Yes.
And since they're transmitting pilots, the base station finds out
Yes,
what the channels look like.
Yes, but
so what are we talking about in the uplink?
so in uplink, no. So basically, it's the same for. I think it's the same for uplink and downlink because because from the interference leaks, you may not have the mechanism of feedback. You may not have the feedback mechanism from your interfering transmitters.
The terminals are telling the base stations what they're seeing for the downlink. So that in the downlink, the base station cooperates and can pre-code correctly so that the terminals can decode their own signal optimally. That I totally understand. But for the uplink, I don't see that issue.
For the uplink, because the transmitter has to know the channel state informations at the crosslinks, right?
Why?
Because he has to know.
Why?
Because he needs to know how much interference is causing to the other receivers, so that he can control the coding speed, so that it does not cause much interference using, so that you can align the interference or align the private interference at the unintended receivers.
That really changed the casting so much. In the three
In the previous case, you want to use interference alignment for each previous case.
I can't get that anymore.
Maybe we can talk about that more. Interference alignment.
To get interference alignment in 1 and 2 units. And we can talk about that offline. Yeah, do you understand what I mean?
Yeah. So, what I want to address here is that you can use the cooperation among base stations to get this channel state information and the transmitters for you, which is the cross-link channel state information. Okay. So let's say that base station 1 can estimate H11 hat and H11